Okay, let's slowly get started. Thank you so much for sticking to the last day. It was a great pleasure for me to, talk about something that's really exciting to me. I hope that you guys also enjoyed some of the topics covered this week. So I guess up to yesterday, we covered some like some topics. We talked about some problems that were motivated by some graph problems like matching, and also like we spent 2 lectures on some modular optimization. And today we'll get a slightly digression from yesterday and the rest of this week. But I kind of felt like so the topics that we talk about today look very practical and useful in practice. That's why I decided to cover these things. And in particular, lecture 11 is about some method that I use for. So it was out of some industry project that I've done with Samsung Electronics. And I realized that, it's kind of, in many practical situations, this method is useful. Okay. And the idea again, I talked about this many times yesterday. The idea is that, the objective that I want to optimize is not given to you. Then it's kind of like if you imagine the matching problem and the integer programming problems where the objective and constraints are given to you, and then your task is to find a solution that satisfies all these constraints while optimizing the objective value. But when the problem parameters are not given to you, then what can you do? So it's not that you are aiming to get an exact optimal solution, but at the same time, you still want to, get a pretty good solution. Okay. That is the main motivation. And in fact, there are, many practical algorithms, and people have tested those algorithms in practice, and they proved empirically that these methods give you a good solution in short amount of time. That's what I'm going to present. But today's lecture is a little bit about, I guess, mostly about continuous work. But the same idea extends to the combinatorial case or the discrete case. It's just that you have to kind of deal with additional techniques to get some like discrete solutions. But even though I'm talking about some continuous word, again, we can apply it to the discrete setting. Okay. All right. I'll introduce what the problem is all about, and I'll give you 3 methods. Well, the first one is it gives you an idea of how it works, and the second one is something that's actually useful. And the last one is a recently developed method using a neural network to learn your function. Okay, so I'm technically giving you 2 different ideas. So one is based on, searching over the solution space. And the idea is instead of just kind of naively enumerating all solutions, can you do something clever than just naive enumeration? That's the first one. The second direction is about, well, because your function is not given to you, but maybe there's some, hidden structural pattern for your function, then can you use like a supervised learning framework to learn your function? And using that, how can you optimize, or can you get a solution that's optimizing your surrogate learned function? That's the second direction. Okay, so so we talked about discrete optimization problems, and I have not even talked about the convex optimization. But let's talk about non-convex optimization problem. Right? Many problems in practice are in fact non-convex, And the function landscape that I want to optimize can look as complicated as this. Okay. Like, this kind of, there are kind of funky landscape, and computing a global minimum, a global optimum can be quite difficult for this kind of complex functions. And it can appear in many situations. And various algorithms were developed for solving, non-convex problems. Like you can apply gradient descent, but gradient descent is guaranteed to find an optimal solution for the convex case. But for the non-convex case, you have to do a little bit of tricks. Like you can you run gradient descent when you converge to a stationary point. Then you might want to kind of perturb your solution using Hessian information, or you can add some random noise to get away from the stationary point. Okay. But still, these algorithms, need, the Hessian information or the gradient. But when your function is not given to you, or it's hard to compute a gradient or compute a Hessian, it's hard to apply these algorithms. So that is the hard situation. In fact, those situations arise in many applications, like engineering design. So like you want to, let's say, design, you want to build a bridge or an aircraft, or you want to design a certain semiconductor chip. What would be the best design that minimizes the electricity cost or something? And it's been used in even machine learning. Like sometimes, let's say you want to run a stochastic gradient descent algorithm, but then you need to choose the right step size. And depending on your choice of step sizes, the convergence rate can, change a lot. So you want to choose these hyperparameters when you run your machine learning models. And also robotics, like you also want to design control algorithms, and whose parameters are quite hard to choose, and how do you choose the right ones? And gaming, game and AI, that's also another example. In finance and trading, like you want to kind of design some trading algorithms that, but the thing is that until you decide on certain portfolio, after you decide on the combination of your portfolio, you can get the actual return. It's hard. Sometimes it's hard to predict the quality of your portfolio before you choose and actually kind of start investing on those financial items. And energy systems, also material science. I think these days people are trying to use AI to design new drug design, like different combinations of materials. That's one example. And healthcare and medicine, and so forth. Okay. There are many problems, but if you look at these things, the issue is that it's not as simple as the matching problem or other like linear programming problems. Like the problem settings, lots of things are hidden, and you want to kind of do something for them. Okay, so again, the point is that the objective function is quite complex, and in many cases they are not even differentiable, and they are noisy in the sense that like when you try the same solution, the outcomes can be different. There can be some random perturbations around your function. And again, because this function is so complex, it's hard to compute your gradient or the Hessian. Okay. So it's hard to apply the known algorithms that are guaranteed to solve a non-convex optimization problem. So it's called, in a technical term, what we are targeting is the following. So it's like we are solving a non-convex optimization problem, but our decision is based on something called the bandit feedback. The bandit feedback means, so you choose your decision, and the only information you can get is its function value. Okay? You cannot use the gradient. You cannot use the Hessian. You only can use the function value. That is what you have. Okay? And such information is called a bandit feedback. If you are already familiar with like the multi-arm bandits problem, what you get is you try certain arm and you get its reward, and that's it. It's not, you're not getting any like further information about the problem or distribution. And this problem is also called a black box optimization. So you choose your decision and you get the function value, and that's it. And based on this information or the history, you choose the next solution that's predicted to guarantee a better solution. Okay. So let's give you a formal, I guess, like mathematical formulation. So we have this optimization problem of minimizing a function, f of x, and C is a domain. I want to solve this. But for black box optimization, just because we don't know, we don't have much understanding about this problem setting, we make minimal assumptions on the problem. We don't assume that the function is convex. We don't assume that it's differentiable or anything. Just there. So we consider the case where the function can be non-convex, and it also can be non-differentiable. So it's hard to assume that there's a gradient information. But in many cases, you can imagine that the function is still continuous, or maybe it can be discontinuous, but the area of discontinuity is not that much for the entire landscape. Okay. You can also imagine that the domain C is a discrete set, or the set of like 0-1 solutions. You can consider that as well. Okay. So the example that we saw, let's get back to this example. Even though it's kind of quite complex, the function is still continuous, and you want to choose the kind of point that gives you a small amount of small value, small objective value. Okay. Any questions so far? Okay. So we make the assumption that the function is Lipschitz continuous. Okay. What it means is the following. So this is one way of modeling, continuous functions. So let's say I pick 2 points, x and y, and I compare their function values. So I measure the gap between f of x and f of y. And if x and y are close, then their functions are close. Function values are close. Okay. This is captured by this inequality. So the right-hand side is, so the gap in the function values is bounded above by the distance between these 2 points, x and y. So when x equals y, the right-hand side becomes 0, and we get 0 value on the left-hand side as well. And L is often called the Lipschitz continuity. So the goal is, we don't expect to find the global optimal solution, but we'll be happy with finding an approximate solution. Okay? I want to find a solution epsilon that has an epsilon additive error to this optimization problem. Okay. So the question is, well, to achieve a certain level of accuracy, how many iterations do I repeat, okay, for this thing? So if you imagine, like, okay, I want to design some like certain biomaterials, like if you test some candidate material, okay, and then you run some experiment to evaluate its quality. Maybe it takes 2 weeks to run the entire experiment. Then the under your budget, maybe the number of possible candidates you can test can be something like 100, maybe, which could take years. So among these 100 candidates, you still want to find the best material design. Okay, so you are allowed to test 100 different candidates. Can you choose a run that's kind of close to the best design? That's the problem. So there is a thing, and what we want is to use is this continuous. Like we want to use this property that the function has some kind of continuous property. So how do we find the approximate solution? Okay, that is the idea. So the naive way is to, again, you globally search over you enumerate all possible points in the solution space and test them. That is a naive way. And let me explain how we do it. So you first discretize. You cannot test infinitely many solutions. So you discretize the solution space. So given your domain C, I get a finite subset C epsilon. Okay, and then you enumerate all points in this domain. That is the first way to do it. So as long as this discretization is refined enough that it has an approximate solution, then I'm good. So you are designing a kind of fine mesh so that the discrete points are they are kind of, I guess, fine enough that it has to, and this one point should be close to the optimal solution. Okay. That's the idea. So the iteration complexity of this algorithm is equal to the number of points in your discretized solution set. You go over every single point and choose the best one. So then discretization has to be important. And I'm showing you one example of how you do it, okay? And this is a naive way. So what I do is the following. Let's say we talk about this 0-1 box, okay? You can imagine something like two-dimensional space and the dimension is 2. And in fact, sometimes when you think about like machine learning models or hyperparameter tuning for neural networks, sometimes your decision variables, like you might have like 3 variables or 5 variables. So we are using these methods for this very low dimensional problems. One variable could be that which optimizer should I use? Should I use Adam or should I use stochastic gradient descent or something like this? This is one variable. Another variable might be what will be the right step size or learning rate. You want to decide. Okay, it's kind of hard to apply this kind of algorithm for the high dimensional problem, but at least for a low dimensional problem, you can apply it. So let's see. So this is a 0-1 box, and the idea is we just discretize the solution space in a way that it gives you some. Now you look at their center points. And so forth. Let's say I have an optimal solution that's contained in this box. Okay. So when you enumerate this box, this particular area, then the point that's coming from this small box will have a kind of approximate value, approximate optimal value, because it's close to, if you look at the points in this box, because it contains an optimal solution, the value coming from that box will be close to the optimality. That is the idea. Okay. But to guarantee the right accuracy value epsilon, you have to decide the number of partitions. That's what I'm going to explain now. So what I'm going to do is I'm going to, for each direction, the number of partition is 1 over L epsilon. That is the epsilon. So when epsilon is very small, the number of partitions will be large. Okay? And in fact, you partition each direction 1 over L epsilon times. So the total number of boxes will be 1 over L epsilon to the D. It's very large. And the idea is basically for each direction you partition so 0, 1, you partition this each 0, 1 interval into the small number of large number of kind of sub intervals with small length. That's the idea. If you do this, each small box will look like this kind of universe, and you take a center point from each small box, and you measure the value of the center point, and the center point is given by this value. Right. So again, the reason that we have to enumerate 1 over L epsilon to the D boxes is because of our design or our choice of this discretization. Okay. You enumerate all the points, and that's gives you. Okay. Right. So we can actually prove that once you enumerate all boxes and take the best solution, and that should achieve the right accuracy level of epsilon. That's based on our assumption that our function is L Lipschitz continuous. Let's just quickly explain it. So because I'm taking small box. Let's say I take an optimal solution right here. Let's say I evaluate the center point containing the optimal solution. Because I'm assuming that this box is small, let's say each direction has length epsilon over L. So the distance between, so you are enumerating at least one point that's close to the optimal solution, and the distance between these two is small. And I use a property that my function is Lipschitz continuous. Okay. You will find you will stumble upon some point that's quite close to the optimal solution, and using the Lipschitz continuity, you can guarantee that this value has epsilon close to the optimal value. So that is the idea. Okay. So that's the that's what we are gonna that's what we have, and we'll get epsilon closed solution to this problem. So we take that center point, and that gives us the solution. Okay, so but there are obviously many issues with this algorithm. You can see that this algorithm is stupid. Like you just have to kind of test many solutions and enumerate all of them. I mean, it theoretically, it gives you a right solution, and it actually you can construct an example that in theory, in the worst case, you actually need to test this many points. Where it is. In theory, you can construct a kind of very bad example for which you need to actually test this many solutions. But in practice, maybe situations can be a lot better. And so naive enumeration does not work well in practice. So can we find some more practical algorithm using some more clever search method? That is our motivation. And then we get back to some issues that are present in this naive discretization. So this is based on a fixed discretization. You just decide on you first decide on how to discretize the solution space, and you run your algorithm and search. But sometimes when you test a certain list of points, you might get an understanding about how this function landscape looks like. Maybe you can use that information. You start searching, testing some points, and you get some function values, and maybe you have an understanding about a possible location that contains this optimal solution. Then you might focus on those small regions and do something. You can make your search more clever in that sense, and practically or empirically, that works much faster than this naive search. That's what I'm trying to do. Another issue is that when you run this fixed discretization, you need to know about the Lipschitz continuity constant. The performance of this algorithm depends on the number of partitions you make, and the number of partitions depend on this parameter L. So you need to know that your function has to be L Lipschitz continuous to run this discretization. But again, I'm assuming that my function is quite complex and complicated. It's hard to kind of understand its property. So this value L is not given to you. And how do you do this? So also, maybe the most critical issue with this approach is that you are assuming the global continuous structure. Your function is Lipschitz continuous over the entire domain of the solutions. Maybe that's too restrictive. Okay. So there are many issues with this algorithm. So motivated by these issues, we got this method called simultaneous optimistic optimization. I'll get into this. So it relies on a weaker assumption than the global Lipschitz continuity assumption. So what we assume is the following. So we assume continuity just around an optimal solution. Okay. Your function might look very complicated, but I just care about the neighborhood around the optimal solution, and I assume that there's somehow some continuous area going on around the optimal solution. That's what I only care about. And also, so that's basically kind of a local Lipschitz continuity assumption. Also, we don't need this constant L here. So I assume that it's Lipschitz continuous around the optimal solution, but I don't need to know this constant L. That's what's good about this method. So how is this possible? Well, again, the previous approach was relying on this constant L when we design this partition. But instead of we decide on the partition first, what we do is we start with a rough partition, okay, and then we start focusing on the areas which could potentially contain the optimal solution, and then we start refining this region. And this method doesn't depend on this Lipschitz continuity parameter. That's what I do. So we gradually refine it, and it is based on something called hierarchical partition. So we partition the area, and then if there's a branch, that's more promising, then we choose this branch, and then we refine this branch by partitioning this area more, and then we keep going on. It's kind of like a tree search-based algorithm. And because it relies on the tree search, it can also be applied to the discrete setting. Okay. So you look at you can create a tree search method for combinatorial solutions. Let's get into what it is. So we first partition this domain into K subsets, and then that will create K children. You are creating K branches every time you choose to partition certain area. So let me explain it. So you first take the domain, and then you partition this domain into 3 subsets, and then you test the values of these 3 setter points. Okay. And then you realize that the last one is promising in the sense that it gives you the best value. Then maybe there's that third region potentially contain an optimal solution. Then let me refine my search by partition this area, and I test the values. Then I realize that maybe this point has a good value, and this point maybe let me use this different color. This blue point, its value is still small, but if you look at this purple region, the region is kind of smaller than the blue region. So maybe there's something more to explore in the blue region because the area is large. Then you might kind of choose more emphasis on the larger region. There's a trade-off between your value and also the area. So you decide on like which to explore. Maybe if you decide on this thing, you can partition this domain, and you get refined subsets. And then you realize that, this area was, I spent enough time on this area, then let me choose something different that has not been explored before. Then I choose this blue region and refine this area. And then I realize that this point part is also promising. Then let me choose to take this area and refine my search, and then you keep going on. We may continue partitioning pieces, and that gives you this kind of gradual partitioning and refinement. Okay. And this can be represented by kind of a tree like this. Okay. So you represent the area and search like a tree, and then you look at let's say this node is the small box that gives you a promising value. Then I can choose to partition this area, and I create 3 branches. Now you look at the current tree, and look at these leaf values. Okay. And then these the points that are in the default level will correspond to smaller regions. Okay. Then you kind of using whatever rule you want to choose. You take one branch and test it, and then you choose to create branches below. Okay. Surprisingly, this method is a lot more clever than the naive enumeration, and it actually gives you a good value in a short amount of time. Okay. So that's the idea, and it doesn't rely on the knowledge of the relationship continuous, because what we do is we choose a certain area, And you can decide on how many branches you are creating by choosing one. It doesn't have to depend on the Lipschitz continuous parameter. And as long as you can keep refining the area, you can run this algorithm. Okay. That's basically what it is. So the idea is you want to choose subsets that are expected to contain an optimal solution. That's the thing. It takes us on the center point. Let me actually move to this thing. But the important idea is based on the optimistic search. Okay. Well, it's kind of that's why this algorithm is called simultaneous optimistic optimization. So you are putting some. So the search is based on two things. Okay. One is maybe it's okay. You might have heard of this trade-off between exploitation and exploration in machine learning. This is kind of a common term in machine learning. That is, let's say you found a box that contains a good value. Okay, then this box is promising. Okay, and another aspect is the following: maybe there's a box, although its value is not that good, but we have not explored this area. Okay? And there could be it's possible that this box, because this is an unexplored area, it covers a large region. It's possible that at some point there's a good value. Okay? And then you are comparing this with a small box which has been explored a lot. Or I know that this value is good, but there's nothing to explore around this region. Even though you choose a small box, this function value will be close to or similar to what we know about this box. Whereas if you look at this big box, it's possible that it contains kind of good value in some hidden location. So you can kind of prioritize over the unexplored area or the box that contains a promising value. So there's a trade-off between these two. Okay, and the optimistic search is to consider these both aspects. Okay. That is the main idea. So we choose to partition something. So it's based on two criteria, which I just explained. So I want to focus on subsets that have good values. Okay, and also if a large subset is not explored yet, then I want to kind of explore this large region also. So this is called the exploration-exploitation trade-off. So like it's kind of similar. I mean, just to explain like what it means in general, I guess. If you become a researcher or a professor, maybe there's some area in which you got your PhD for. Okay, you are already familiar with this area. Then if you just focus on this area, then you can get some good results pretty soon. But maybe there's another area that you are not familiar with. But if you kind of spend some time on there, it's possible that you get something good out of it. And you can explore this new area, or you can just kind of focus on whatever you are already familiar with, this exploitation. There's a trade-off between these two. Okay? Maybe like if you do something in the new area, it might take more time to get used to it and get good result out of it. But maybe after spending some time, it's possible that you get some good results. So there's a trade-off between these two. So that's the same principle is being used in this search method. Okay. So there's a formalism. Like when there's a kind of good measure, you basically have so this trade-off or these two criteria can be considered as considered by some kind of nice mathematical expression. So you are choosing the one that's minimizing the loss, the maximizing the value, objective value, plus the area of the current region. So you are putting the emphasis on a large region, and at the same time, you are putting the emphasis on the function value. So by optimizing this value, you choose the one that's promising. That is the idea. Let me actually move on. So you run the algorithm, and so here, I guess the function value, you choose the one. Yeah, I guess like I spend here. So we. Yeah. Let me actually back to this thing. Yeah. Any question?
I have a question. Consistency of the local resistance. Is there a relationship between the local resistance and the partition such or just the resistance for the derivative?
So we can prove that. So there's a okay. This is not just like empirical. There you can establish some like theoretical guarantees of this algorithm, like in terms of convergence. So the convergence. So to derive the convergence result, you need to you don't have to assume the global Lipschitz condition. As long as you have a local Lipschitz continuity property around the optimal solution, then you can derive that convergence rate.
Then to converge this parallel convergence is necessary.
Right. So this hierarchical partitioning is necessary, and I guess like I didn't explain like how to choose this. I mean, I explained the intuitions behind this exploration and exploitation, but there's a way of doing it. So I mean, there's a like some sophisticated mathematical expression, and based on that, you search it. So that's important, and then also the hierarchy, how you partition the things is also important. And there's this notion of near optimality dimension, and your convergence guarantee will depend on this notion of the near optimality dimension. And if you assume this, you can guarantee the convergence rate. There's a finite convergence rate. That is, after this lecture, I'll upload my paper, a recent paper of one of my students, and it's about it's more. So our result is about some stochastic setting. You could also have some noisy evaluations. So like when you test some point, there's some randomness of this function evaluations. We design an algorithm for those things. Yeah.
그 파티션 개수는 지금 그냥 K라고 하셨는데 이게 원래 디멘전에 의존하게 해야 되나요? 아니면 그냥 아무렇게나 해도 상관없나요?
It has to depend on the dimension. So it will be. I mean, if you apply the Euclidean case, the number of partitions will depend on the dimension, like 2 to the d. So if you so it's kind of hard to apply this algorithm to like high dimensional problem. But you can apply this algorithm to like maybe 10-dimensional problems or 20-dimensional problems. But as soon as you do that, the number goes exponentially. Yeah, but I guess the point is that we are already dealing with very complex, very complicated problems, and there's nothing we can do other than the search, and we are making the search more practical. And I guess that is like we cannot hope for something as good as like gradient descent or stochastic gradient descent. Any other question? And one good thing about this approach is that there are nice implementations that are available on the web. Okay, like, let's say you are working on some industry problems, and it turns out that there are lots of. It turns out that those problems are too complex that there's no way to solve it other than black box optimization frameworks. Then you can Google this method, and there are nice kind of software implementation about it, and you can use it. That's all right. Great. Let's move on to the second part. This is kind of recent. So, like in the previous part, we didn't assume any structure on the function. Okay, what we done was our focus was on the solution space. We were searching over the solution space, and then we were just exploring the area, and then we found certain locations that are promising. Okay? And this one, well, it's not like, so this method doesn't really understand the structure of the function. We are just searching, we're just yeah. And the second method is about learning the hidden pattern about your function based on the data. It's a learning-based algorithm. That's what I want to explain. Again, we don't have access to any of this information. We don't have access to the gradient. We don't have access to the Hessian information. But we learn the function values, function landscape based on our bandit feedback, and that's what we want to do. And let me move on. So optimistic optimizations is good because it relies on minimal assumptions, but maybe sometimes your function is, although you don't know the structure in advance, you still want to use some properties. It's just that maybe that there are some structures, but just that we don't know about it. But when you collect more and more data, maybe you get to learn the structure and discover the structure, and you can use it. Okay. So that's what we are doing, and so the goal is to exploit any underlying structure of your functions. That's what we are trying to do here. Okay, so the question is, how do we explore the unknown structure that we can learn from the history of our solutions? That's based on we're gonna use the supervised learning method. So we test a sequence of solutions and collect their function values, and we use those data to infer the function value for unknown or untested points. That's what we are going to do. So let's say you learn the function model, and by optimizing that learned model, you can predict a good solution later. That's the method. And how do we? So let's say we have n data points. I have tested a sequence of n solutions, and I know their function values. And how do I do this? So I guess in practice, you might want to use a neural network as a model to approximate your solution, your function. So we are solving this. So F data is a neural network, with parameters data. I'm hidden these values here as just data, but imagine that like you're designing, you have a neural network with certain number of layers. In practice, you typically use a single hidden layer neural network, and it turns out to work well. But we want to decide on the weight of these connections, and that's captured by this parameter data. And how you adjust the weight of your neural network, you are solving this optimization problem with a loss function. Okay, that's just how we do it. So after training your neural network, which gives you some model F data that works as an approximate function for your unknown objective function. If you have kind of some chunk of data about your function evaluations, then it gives you a good approximation. That's what we are gonna do. So then the real question that I'm interested in today is, let's say I use some method to train my neural network. Then my next question is, how do I find a solution that optimizes this learned model? Okay. And then what we care about are neural networks. Okay. That's what's been used in many situations. But if you imagine a neural network, it's a non-linear function. Let's say I'm solving a combinatorial optimization problem. I'm choosing the best 0-1 vector that optimizes on non-linear function. And then if this turns out to be a submodular function, like we talked about some algorithms to minimize the submodular function or maximize the submodular function. But a neural network doesn't give you a submodular function, or it doesn't give you anything kind of well structured. It's complex. It's highly nonlinear and highly non-convex. And how do you find the one that optimizes this function? And I'm going to show you like how to do it, how to optimize it using an integer programming model. So the idea is, if you imagine a neural network, it's like a piecewise linear functions. Okay, it's kind of combination of linear functions using some activation functions, and that can be solved by an integer program. That's what I'm going to present. Okay. All right, so that's what it is. So it's due to so in fact, for black box optimization, in many situations you're not using something as complex as a transformer. Maybe it's like a kind of simple neural network, a feed-forward network, like multi-layer perceptron is enough to capture an unknown pattern. So I'm gonna focus on the setting of feed-forward network, maybe a single layer. Okay, and how do I choose a solution? And typically, like we use like value activation functions. Okay, that's like we're gonna explain the basic formulation by Fischetti and Joe. But we got some recent development improvement over this works, but the idea is still there in the future in the later works. I'm gonna explain how we do it. So we're gonna focus on single hidden layer case. So I have input x1, x2, and xd. So these are my feature variables, x1 through xd, and I have a single layer, and you get an output right here. This is the output layer. What you do is, let's say this is the ICE neuron. Okay, then you add these connections to the ICE neuron, and the value here is let's say WI1, WI2, WI3, all the way up to WID. Okay. So the ith neuron in the hidden layer receives this value of summation of j from 1 to d, wi j, xj. You aggregate these weighted variables, and this is in fact just maybe you possibly have some the bias term which is present before, and this is equal to WI transpose X plus BI. Okay. It's single, its neuron, ith neuron has this weight vector WI, and it receives the input values, and you take the inner product with that and add a bias term BI. Okay. Now, but then you use and then the ith neuron returns a value to the output neuron, and the value that it's outputting is you apply your activation function sigma. In this case, I'm gonna move on to this thing. This is the activation, and you are outputting into output neuron. So this is you're applying the value activation. So the value that the ith neuron output is value of WI transpose X plus BI. And the ith neuron is attached to the output neuron. Let's say there's a weight of AI, small AI. So the output neuron will receive summation I from 1 to K. Let's say I have K neurons in the hidden layer. Then the final value of the output neuron is AI times the value of WI transpose X plus BI. This is what we receive. So this is the approximate model, approximate function, the function of that approximates my original objective function. So I want to choose a decision variable X that minimize this function, the approximate function. You can where X is coming from my domain C. C can be, for example, a set of 0, 1 points satisfying certain solutions. Can be a matching from your graph. But the question is that we have this non-linear objective. And the question is, how do we solve this thing? Is there any question? Okay, so that's what I just explained. So the final, the model is given here. You get this neural network. So if you choose a certain decision vector X, that its value is approximated by this output. So now the question is, how do you minimize this value? And I have just added this, replaced this TI. I haven't added this auxiliary variable TI to replace the output of the value activation function. Any question? Good. So okay, now let's kind of recap about what I've just explained. So let's say we have an unknown function f, or we have a history of function evaluations. So using this data, we train a neural network, and our trained neural network is given by this expression. So we have trained the weights, WIs, AIs, and BIs. So we have trained this, decided on this weight values. So this gives you an approximate function. Now the question is, okay, I have this learned model. What is my next candidate solution? I have approximated the objective function. We have this learned model, and by optimizing this function instead of the original objective function, I can choose kind of potentially a good solution. And the question is, we need to optimize this function. We need to have a way of optimizing this function. This can be a difficult problem, again, because this function is nonlinear. So, and then I have written down the same optimization problem with a linear objective. I have to linearize the objective function using a variable. So that was the part. But now, I'm going to explain that you can rewrite this optimization problem as an integer linear program. That's what I'm going to explain. Okay. And the idea is the following. So if you look at value, the right-hand side, if you forget about this value activation function, you have this linear function, a wi transpose x plus bi. Okay. And at the same time, value is basically, if x is negative, then it has value 0. And as soon as it becomes positive, it takes value x. So it's like a piecewise linear function, even value. So you're taking a composition of a piecewise linear function and a linear function. It's almost like a linear function for value. So we use that idea, and it turns out that we can replace this thing using some integer variable with linear constraints. That's what I'm going to do. So we assume that there are some lower bounds and upper bounds, global lower bound and upper bound on this value of the linear function wi transpose x plus bi. Okay, we have this information. Then I can replace this constraint that ti equals the result of this value activation function as follows. Okay. Let me write down 4 linear inequalities with some binary variable. And I'll explain that these 4 inequalities safely replaces this constraint. Okay. All right. So ti, first of all, it has to be non-negative. That's because this is the output of value. And also ti is at least wi transpose x plus bi. If it's negative, I can't take the value 0. If it's positive, I take this value. So I have this condition. And also, I have ti at most ui times zi. I will explain what it is. So zi is (0, 1), and ti is less than or equal to wi transpose x plus bi minus li times 1 minus gi. When zi equals 0, then you get 0 here. And we use color black. Oh no. We have 0. When zi equals 0, wait. All right, so it's been the last inequality will be Wi transpose X plus Bi minus Li. When Gi equals 1, you have Ui, but you have Wi transpose X plus Bi. Okay. And you know, this thing is strictly positive, less than or equal, greater than or equal to 0, because Li is the minimum value. So when Gi equals 0, it means that Ti equals 0 by this constraint. And when Gi equals 1, we have Ti equals Wi transpose X plus Bi. So these binary variables, Gi, you know, considers this kind of two disjoint cases. Ti can be 0, or Ti can be Wi transpose X plus Bi. This is what it is. So using this, we can rewrite the problem as follows. So we are minimizing summation I from 1 to k ai times ti, subject to, we just write down the inequalities we have just found. Ti is less than or equal to ui gi, and ti is less than or equal to Wi transpose X plus Bi minus Li times 1 minus Gi, and Gi is 0, 1. And you could also have some constraints for X. X belongs to C. So I for K. Okay. Again, C can capture some integer constraints on your variables X. Okay. And also other linear constraints to model your solution space. And up to adding a linear number of linear constraints with binary variables, you can, you know, optimize this neural network, or you can find a solution that's optimizing this neural network. That's what it is. Okay. And you know, this formulation can, I have just explained the single hidden layer case, but you can extend this idea to multiple hidden layers. That's not too difficult. And in fact, you know, that was this was the very first formulation, but there are some better formulation in terms of, you know, computations were developed recently after the first development. And I think it's one of kind of central questions in combinatorial optimization to, I guess, to improve this formulation and get a better one. Any questions? Okay. Now let's stop here and we meet again at 11.